So we've been dealing with derivatives and limits all semester, and now we're going to jump into what are called antiderivatives. We saw a little bit of this back when we were doing the mean value theorem. They had thrown in some questions about thinking backwards. What function could we take the derivative of to get this function back? And so let's just look at what the antiderivative is. Let's kind of go through and think about it and kind of think about how we can come up with some formula that would give us this antiderivative. So we say a function, and normally we call antiderivatives, we denote it with a capital letter. So a function f is an antiderivative of the little function f on some interval I if we take the derivative of that capital letter, f of x, of that antiderivative, and it gives us back the original function f of x for all x on I. Okay, and so I had already mentioned this down here below, some of this, but let me just read through this too. So the process of recovering the function capital F of x, antiderivative of f of x from its derivative f of x is called antidifferentiation. We use capital letters such as capital F to represent the antiderivative of little f and capital G to represent the antiderivative of little g and so forth. So I want you to take a couple, or I was going to say a couple of minutes, but maybe a minute to look at these functions f of x, g of x, and h of x, and see if you can come up with something that you would take the derivative of to get these functions back. So I'm going to pause the video, and if you're watching this not live, then you pause your video and think about it. Okay, so you had a moment to kind of think about this, and some of you chimed in with what you got, and you did a great job. So let's go through and talk about how we would find the antiderivative of these. And so really we have to go back and think about the derivative, because we were trying to find something again that if we take the derivative of what we're finding, we would get this. And so we know that we bring our power down front of x. And so we want this 2 here. We know that we could have a power of 2. And so I would think to myself, now if I took the derivative of that x squared, what would I get? And we would get back that 2x. And so that antiderivative, we can say, is x squared. And again, we can show this by taking the derivative of the antiderivative. We get back 2x, which was the same thing as our little f of x. So some of you even went further and you said, okay, well, couldn't we take the derivative? Let's say we chose f of x to equal x squared plus 10. If we took the derivative of that antiderivative, this would equal derivative of x squared is 2x, and a derivative of a constant is 0. So that still gives me back my little f of x. But that means, right, can I add any constant in there? Because when I take the derivative of a constant, that's going to go back to 0. And so right now, a lot of times we're going to add that c in there. We're going to add that in there until we get into definite integrals, and we'll talk about that later this week. But right now, or next week actually, for right now, we're going to just add this constant. If you think about it, let's just think about it geometrically really quickly. If you think about what does the graph of y equals 2x looks like? Actually, we can also think about what is the graph of x squared looks like. Let's do that instead. Remember, if you added or subtracted a constant and you were thinking about transformation of functions, that just shift our function up or down. So if we added some constant c here, we would have the same shape, but it would just be shifted up. Same thing as we took some value and we subtracted some constant. Just call it c sub 1. So that would take our original function y equals f of x, and that would just shift it down c sub 1 units. So same shape. Pretend that is J. Actually, I know how to make it the same. Technology could be great. Maybe. Maybe not. I was going to say we could just pull this function, right? But it won't do it. Okay, I can play with that when I'm not doing a video. Okay, so let's do this. Same shape, we just shifted down c sub 1 units. If I took and looked at the equation of the tangent line anywhere, so let's say right here, how about, let's say this is x of 0. And I looked at the tangent line right here on my original function. That's going to be the same tangent line at x sub 1 as I get here. The slope is the same at those values. So pretend those are all parallel lines. I'm trying to do the best I can. So we know that that equation or that slope at each of those pieces is going to be the same at that value. And so again, that's why we're adding that constant in there. So that's kind of the geometric approach of that. So let's go and look at the other ones. So looking at this, we have g of x, little g of x is equal to cosine of x. So we want to think about what can we take the derivative of to get back positive cosine of x. Well, remember taking the derivative of sine x, that was positive cosine of x. And so we can say that the antiderivative of g of x, which is cosine of x, the antiderivative is sine x. Again, if we take the derivative of that, and we can add a constant c here. So if we took the derivative of sine of x again is cosine of x, derivative of a constant is 0. So this last one, we're trying to figure out what we can take the antiderivative of to get back 1 over x plus 2 e to the 2x. So thinking about it, what can you take the derivative of? What did we take the derivative of to get back 1 over x? Well, recall that's the natural log of x. We need an absolute value there. Unless we know that x is positive. So it's equal to the natural log of x plus, and so now we got to think about this 2e to the 2x. So when we take the derivative of 2e to the 2x, that would give me, remember e was the derivative was itself. And times the derivative of the numerator, that's not the numerator, of the exponent, 2x, which gives me back this 2. So plus c. Awesome. Good job, guys. So again, we can test this. So they might tell you in your homework or on a problem, here is the antiderivative. Show me it's the antiderivative of this function. So you're taking the derivative of the antiderivative and showing you get back that function. So derivative of natural log of x is derivative of natural log is 1 over what you're taking the natural log of, which is x, times the derivative of the inside, which is just 1, plus the derivative of e to the 2x using the chain rule. Derivative of the outer is e to the 2x. E is just itself. Inner is 2x. Derivative of 2x is 2. Derivative of constant is 0. So any questions on that? Okay, so we have an important theorem, and that states if the antiderivative, capital F, is the antiderivative of little f on an interval, capital I, then the most general antiderivative of little f on I is capital F of x plus c, where c is some arbitrary constant. And we discussed that just a couple minutes ago when we were looking at why we would add some constant graphically. So to help us kind of find the formulas or looking at the formulas or how we get the formulas, it's kind of nice to go back and actually just look at formulas for derivatives. So the derivative of constant we know is 0. And so that's why we put that plus c when we do the antiderivative, because we know when we take the derivative of that antiderivative, we're going to get 0 for that constant. But here, let's look at this. So if we have the derivative of x is 1, so going backwards, so we're trying to think about what could give me the derivative of 1, which would just be x, right? Well, what would the derivative of 2, or what could give me the, what if I took the derivative could give me back 2? So if f of x was 2, then my antiderivative, what would get that back would be 2x. If my function f of x was any constant, c, then whatever I would take the derivative just to get that constant would have to be c times x. And then let's look at powers. If I have something, let's say f of x is equal to x cubed. Well, I know when I take the derivative, I am going to get one less exponent. So let's think about this logically, because the antiderivative is, okay, if I take the derivative of that, I want to get back this x cubed. And so we know that we're going to be subtracting 1 from our exponent up here. So let's just add 1. So thinking about this, okay, well, now if I took the derivative of this, I would be bringing down my power down front, and I would have this 4x, and then I would subtract 1 from my exponents. That would be okay for this piece, but this 4 in front, I don't want, because our coefficient in front of the original one is 1. So kind of thinking about it backwards, what would undo that process of that 4 in front would be dividing by what my exponent is. Let's ignore the c for a second, that constant. So if I take that derivative now, we can use the rules, bring down our power down front. I get my 4x, subtract 1 from my power. I get my cubed all over 4. And so think simplify, and we can see that that gives me back my original function, x cubed. So thinking about it again, to get one exponent lower, we said we were going to have to add one to our exponent. So let's say f of x is equal to x raised to the nth power. The antiderivative, to get one less, we would have to add one to the original. So I would have n plus 1. But thinking about, okay, when I take the derivative of this, I would have to have that coefficient of what my exponent originally is. Well, I don't want that. I want a 1 in this case. And so if I divide by my new exponent that I just decided, then when I do bring down my exponent, when I take the derivative, it would cancel that out. And we can add some constant c. And get back our original. Okay, so we're coming up with some rules to help us. So another one is talking about our trig functions. We just saw sine of x, but what about cosine of x? Remember, when we take the derivative of a cosine of x, we get back negative sine x. Well, so I'm trying to think, okay, and if I take the derivative of sine x, I get back what? I get back cosine of x. So I'm trying to think what I take the derivative of to get back cosine of x would be sine x. And then a plus c. We did that one wrong before. So if we had g of x was sine of x, the derivative to get sine x is cosine of x will give me negative sine of x, but I don't want the negative in front. So I would have to compensate for that and have a negative out front. And so taking that derivative would work. That would give me negative sine x, which is sine x. Okay. So then it's just recognizing stuff like that we talked about with the natural log, knowing that I would take the derivative of 1 over x, and that would, the derivative of natural log of x is 1 over x. Okay. So let me just pull up our rules, and then let's do some problems. Actually, before we pull up those rules, let's do some problems from your book. Let me get some space to see if we can think about it without any of these formulas. So we're just quickly looking at some of the beginning problems in our textbook at the end of this section, and looking at problems 1 through 24, A through C. You should be able to try to come up with these without So find the antiderivative for each function. Do as many as you can mentally. So without any of the formulas yet, could you figure those out? So I just want you to look at it for a couple minutes and kind of play with it and see. And then let's go through and look at some of these. Okay, so first one is 2x. Trying to think, what can we take the antiderivative of to get back 2x? And so let's just call it y, actually, or capital F. If we took the derivative of x squared, we know we get back 2x plus some c. So quickly taking the derivative, that's 2x, so that works. So let's call this g. So the antiderivative of x squared, well, we kind of talked about this before. We need to get back an x squared when we take the derivative. So I need one higher for my exponent. And if I took the derivative right now, just of x cubed, I'd have this 3x squared. And I don't want a 3 in front of my x squared. So we could compensate by dividing by my new power, plus c. So taking the derivative really quickly, bringing down our power would give us 3x. And then subtract 1 from our exponent, we get squared over 3. Derivative of a constant is 0. Those cancel. And our antiderivative is equal to our original function of x squared. So for part C, same sort of idea, we just have more than one term. Well, remember when we're taking the derivative of a sum or a difference of terms, we could just take the derivative of each piece. So same sort of idea here. So let's say that this was h of x. So the antiderivative of h, capital, and we denote it by capital h of x. So again, something that we could take the derivative of and get back x squared. Well, we just did that. That was just x cubed over 3. Doesn't matter if I add a constant here. If I add a constant to all 3 pieces when I take the antiderivative, summing those constant is still another constant. So I'm going to just add one constant when I'm finding these antiderivatives of multiple terms. Okay, so minus, I need this minus sign. I know I need to get a 2 in front. Oh, well, we already did this piece, right? All over here. So what I took the derivative of to get back 2x is x squared. Plus, when I take the derivative of to get back 1, well, if I take the derivative of x, I get back 1. So plus c. Quickly, you should be able to check it. Take the derivative. We should get back this little h of x, x squared minus 2x plus 1, which we do. So let's maybe pull a little bit of a harder problem. What if we had 4/3 the cubed root of x? I prefer to name these. Let's just say this is 2, and let's call this f of x. No. So unfortunately, I didn't have the correct screen on when I was just talking through all those pieces, but I hope that you could follow along. If not, just pause the video and look at it and think about it. Write it down. You can rewind the video and then watch as I explain it. I guess you could do that too. Okay, so our next example is little f of x is equal to 4/3 and then times cubed root of x. And so again, we want to find what we can take the derivative of to get that back. Just give myself some more room. Okay, so let's rewrite this. Just like when we were taking derivative with radicals, we rewrote it with the an equivalent form, but exponential form. So we have 4/3 x to the 1/3. So again, we have to think about this backwards. Well, we know we're going to subtract 1 from our exponent, so we need to compensate, and we could add 1 to that. So if I add 1 to 1/3, I get back 4/3. Now I think to myself, well, if I take the derivative of this now, that would give me what's in front, and that's what I want. So we can leave it alone. We don't have to compensate by dividing, but we just, by what we had just created as our new exponent. What about f of x equals secant x tan x? So what can we take the derivative of that would get us back secant x tan x? What we can take the derivative of to get back secant x tan x. Isn't that secant x? And then plus c. Let's say I don't remember. So let's check it. I'm going to rewrite it because I know what the derivative of cosines and sine is. So I can rewrite this as 1 over cosine of x plus c. I don't want to have to use the quotient rule, so let's rewrite this. This is the same thing as cosine of x, all raised to the -1 power, which is not the same as the inverse function of cosine plus c. Now I could just use my chain rule, bring my power down front, -1. So that isn't right, is it? Let me just do it. Cosine of x, derivative of the inside, cosine of x. Subtract 1 from my exponent, -2 times the derivative of the inside. So the derivative of cosine of x is negative sine x. So let's rewrite this. Notice I have a negative and a negative. That's a positive. I'm going to have a sine x in my numerator because that doesn't have a negative exponent, all over cosine of x quantity squared, which I'm going to rewrite as cosine of x times 1 over cosine of x. Well, sine over cosine, that's tangent. And 1 over cosine is secant. Okay. So the antiderivative of secant x tan x is secant x. And I just showed it. Okay, so let me show you a table of antiderivatives. And so it's helpful if you know move backwards, what your derivatives are. So we had discussed number 1 in here. If our function is x to the n, if we take the antiderivative, we're going to add 1 to our exponent. We're going to divide by our new exponent, and we add some constant c. So I did not give you the stipulation that n can't be -1. If n is -1, we get back 1 over x, right? If I have x to the -1 power, that's the same thing as 1 over x. So what we take the derivative of to get 1 over x is that natural log of x plus a constant. X can't be 0 because it's undefined there. So that's why we have the stipulation in here that n can't be -1. We talked about the trig functions a little bit, but we didn't talk about it with having some coefficient times x. So like this sine of k times x. Well, when we take the derivative of something that has this argument is not just the variable, you have a coefficient in front of that variable, we had to apply the chain rule. And that chain rule, we would take the derivative of the inside, and that derivative of the inside would have this k come out front. And we want a coefficient of 1 here, so we compensate for that by, when we're doing the antiderivative, we divide by this. Okay. So we could go through and we could talk about all these, but I'm not going to do that. We'll talk about them as we come across them in problems. So just a couple things that you hopefully noticed while we were doing this. Constant multiple rule. Same thing like when we were doing derivatives. If I had the derivative of some coefficient times x to the n power, I could first take the derivative of x to the n and then multiply it by that coefficient. Same idea here. If our function we want to get back is k f of x, I can ignore that coefficient in front at first, figure out what that antiderivative of f of x is, and then multiply it by that coefficient plus some constant c. We looked at it when we were talking about the example, the sum and difference rule. So same idea that we had with derivatives, we have with antiderivatives. So if our function is little f of x plus or minus g of x, sum or difference of terms, we can name each term a function, then the antiderivative is capital F of x plus or minus capital G of x plus that constant c. Okay, so let's look at an example. So we have little f of x is equal to 1 plus 4 over 3x minus 1 over x squared. And we want to find the antiderivative of f of x. So let's just do it in pieces, ignoring the plus c until the end. So thinking to ourselves, what can we take the derivative of to get back 1? Well, we know the derivative of just x is 1. This is where we need to be a little bit careful. And maybe let's rewrite before we look at this function a little bit. All right. Let's do it this way. So let's rewrite that. This is f of x equals 1 plus 4/3. I'm going to leave that as 1/x minus x to the -2. Remember, we're back in the rules that I just gave you. It said if x is -1, if that exponent is to the -1 power, that rule didn't work. So thinking to ourselves, let's just, constant rule, we can leave that 4/3, that constant in front, alone, and thinking to ourselves what we take the derivative of to get back 1/x is the natural log of x. So natural log absolute value of x. Minus, so thinking to ourselves again, what would I take the derivative of to get back x to the -2 power? Well, remember, we're going to subtract 1 from our exponent, so we're going to add 1 to our exponent. So if I add 1 to my exponent of -2, I get back -1. And then I divide by my new exponent, -1. And then I need that plus c. So this is x plus 4/3 natural log of x. A negative and a negative, so I'm going to have a plus x to the -1 plus c. So let's check. So that could be a good test question. I want you to find the antiderivative. Now I want you to show me by checking it that you found the correct answer. So checking it, you're going to find the derivative and show that we get this back once we take the derivative. And so I'm going to take the derivative of x, which I know is 1, plus 4/3. Derivative of the natural log of x is 1 over what we're taking the natural log of, which is x. Taking the derivative of x to the -1, I have to bring my exponent down front, negative x, subtract 1 from my exponent, -2, and that derivative of the constant is 0. And right away, I noticed that this is the exact same thing because I could make this exponent positive by bringing it down into the numerator. So the derivative of our antiderivative is 1 plus 4/3x minus 1/x². I would probably clean up my antiderivative just a little bit because our original function didn't have negative exponents. I just wanted to leave it in that form when I did my check. So I would write my antiderivative as x plus 4/3 natural log of x, absolute value of x, plus 1/x plus c. So now let's get into some notation. So when we took derivatives, we had different notation, right? We could write it with that prime symbol. So if it was little f of x was our function, when we took the derivative, we could write it as f prime of x, or we could write it as df over dx, df dx. There was just multiple ways to do that. Same sort of idea when we're taking the antiderivative. There's different ways that we can notate that we're taking the antiderivative of a function. So instead of having to state each time, we'll find the antiderivative of this, we can look at it a little differently. And this is where indefinite integrals come in. So indefinite integrals, that's just telling us that we're taking the antiderivative of our function. We'll get into what is called definite integrals next week. But for now, we might actually touch it at the end of this week, but for now, we're just going to look at indefinite integrals. The difference is if it was a definite integral, I would have some number down here at the bottom of this sign. It's like an elongated S symbol, which actually is kind of going to get to the point of why we use that tomorrow, because we're summing a lot of rectangles. We'll get to that tomorrow. But if it had a number on the top and the bottom of this S symbol, that would have been a definite integral. But we're not dealing with those yet. We're just dealing with indefinite integrals. We don't have bounds on our integration. So let's just read through this. So the special symbol is used to denote the collection of all antiderivatives of a function f. So the collection of all antiderivatives of our function f is called the indefinite integral of f with respect to x, and is denoted with this integration sign, which is that elongated S of little f of x dx. That little or elongated S symbol, that is called the integral sign. The function f is called the integrand of the integral, and x is the variable of integration. This right here is telling us what we're integrating with respect to. So if this had been dt, that would be telling me I'm taking the integral of this function with respect to t. And this function right here doesn't have a t in here, so I could treat that differently, but we're not going to look at that right now. But that symbol again, dx, that's telling us what we're taking the antiderivative of. Okay, so let's look at some examples of finding indefinite integrals. Okay, so we have the integral here of x raised to the negative 3 power, all times the quantity x plus 1, and then dx. So we're trying to find the indefinite integral of this. So just like when we were starting to find derivatives, a lot of times it wasn't in the form that we could take the derivative right away. We didn't know the quotient or product rule. We a lot of times expanded it. So same sort of idea with taking the antiderivatives. Sometimes we're going to have to rewrite it to be able to find the antiderivative. And so let's first start here by distributing x to the negative 3 power. So doing that, we get rules of exponents. So x to the negative 3 times x to the first. That rule, same base, we add our exponent. So that's going to give me x to the negative 2 power. Negative 3 plus 1 is negative 2. Distribute x to the negative 3 to the positive 1. I get plus x to the negative 3. And then we have dx. Notice I had put parentheses around this whole thing, because technically if I didn't do that, it's not written mathematically correct. Okay, so I'm going to drop this integral symbol once I take the antiderivative. And so recall, so another way we can write this, the antiderivative of x to the n dx, we added 1 to our exponent, so n plus 1, divided by our new exponent and added c. So doing that, adding 1 to my exponent, so negative 2 plus 1 is negative 1, divide by my new exponent, negative 1, plus, so adding 1 to my exponent, that gives me x to the negative 3 plus 1 power, gives me negative 2 power, divide by my new exponent of negative 2, and then plus some constant c. So let's call this capital F of x. This is the same thing as negative x to the negative 1 minus 1/2 x to the negative 2 plus c. So let's check it. So we want to show that the derivative of this is equal to little f of x, where little f of x is our integrand, which is x to the negative 3 parentheses x plus 1. Okay, so that's what we're trying to show. So let's take the derivative. I'll leave it in this form for now. Taking the derivative here, bringing down our power down front, -1 times -1, that's +1. X, subtract 1 from our power, that's a -2. Minus our coefficient 1/2. Bring our power down front, so that's a -2. Add 1 to our exponent, so -2 plus 1 is -1. And the derivative of a constant is 0. So this is x to the -2. Notice our 2's cancel here. And we have a negative and a negative, so we have a plus x to the -1. So we haven't really done exactly what we wanted to do yet, quite yet. And do we have a problem? I didn't subtract 1 from my exponent, did I? Darn it, I do have a problem. First of all, I didn't put my symbol. Oh. What did I do wrong? This should have been x to the -3 power in here. Let me just see. Right here, when I subtract 1 from my exponent of -2, -2 minus 1 is -3. -3. Which is the exact same thing that we have right here, which is our integrand. We could, if we wanted to, just like we had distributed here, we could factor out an x to the -3 power. If we factor out an x to the -3, we have to think to ourselves, what do we need? So, and we would add exponents to get back a -2 power. Well, that would have to be a +1 power, x to the first. When we pulled out an x to the -3 from this, so this is +1. Which is the same thing as little f of x. So we showed it. So next example, we're integrating. Our indefinite integral is in the numerator 4 plus the square root of t all over t cubed dt. So right now, I don't know how to integrate this, but I can manipulate this so that I can integrate it. So same idea as what we were doing with differentiation. At first, we didn't know what the quotient rule was, and so we would rewrite it. If it was only divided by one term, we could rewrite this as 4 over t cubed plus I'm going to rewrite the square root of t as t to the 1/2 over t cubed, parentheses dt. So rewriting it, I can rewrite 4 over t cubed is the same thing as 4 times t raised to the -3 power, plus, so using rules of exponent, division, same base, I subtract. So this will be t 1/2 minus 3, which I know I'm going to need the common denominator, 2/2 dt. So I'm integrating 4t to the -3rd plus t raised to the 1/2 minus 6/2 is -5/2 dt. Okay, so taking the antiderivative of this first term, I leave my coefficient alone at first, this 4. I'm just looking at t to the -3rd power. So if I add 1 to my exponent, -3 plus 1 gives me -2, and I'm dividing by my new exponent of -2. Plus, so t to the, I have to add 1 to my exponent. So because it's the fraction, I'm just going to add 1 here, 2/2. And I'm going to divide by my new exponent. Well, now that I can see it, -5/2 plus 2/2 is -3/2. And then I need my plus c. So let's simplify this down and rewrite it. So notice I have a 4 and a -2. So 2 goes into 2 once, 2 goes into 4 twice. So right now, rewriting this first term, I have a -2, and I'm going to make this exponent positive by bringing it down to the denominator. So all over t squared. I don't like that I'm dividing by a fraction, so I can invert multiply. Same thing as multiplying by -2/3. So this will be minus, because of this negative. Flip it, so 2/3 t to the, well, -5/2 plus 2/2, we said was -3/2 plus c. Again, we can clean it up a little bit. So -2 over t squared minus 2/3. Let's rewrite it so that doesn't have a negative exponent. So this is going to be the same thing as t to the 3/2 plus c. Really, I would leave it like that. We could, if we wanted to, go ahead and rewrite it so that it's a single fraction, but I don't think that that's going to help us. So let's just leave it like this. We can use the radical because that one had a radical. So t to the 3/2 is the same thing as square root of t cubed. So this is the end of chapter 4. And we're going to get into another way to look at antiderivatives tomorrow. Actually,